So now I want to discuss what happens as a reaction proceeds. We know that reactant and product concentrations will change. We know that that will affect Q, and we know that that in turn will affect the voltage according to the Nernst equation. But we also know from way back earlier in this class that eventually a reaction effectively stops, right? And that's what we call equilibrium. What is the voltage when we've reached that condition? The answer is 0. So let's write this. At equilibrium, reactions stop. We know that from earlier. But what that translates to is our voltage is now equal to 0. In other words, it is no longer energetically favorable, nor is it unfavorable to proceed. It's just done. The electrochemical cell is dead. Another thing that we can say is that at equilibrium, Q is officially equal to K, because remember, they're the exact same expression. It's just that K is whatever that expression equals specifically at equilibrium, which is the condition that we're currently discussing. And so with those 2 points, we can manipulate the Nernst equation to get the following formula. Manipulate Nernst equation to get the following formula. K, i.e. our equilibrium constant, is equal to 10 to the n E standard state divided by 0.05916. What this equation allows us to do is determine the equilibrium constant for a reaction based on the overall standard state voltage, which we can measure or look up if it's already been measured by someone else. And this right here, believe it or not, is the Nernst equation with these values plugged in appropriately and some algebraic manipulation. And we'll make a note that this math is on slide 9. Math on slide 9. Let's quickly check that out. Now, you don't need to be able to reproduce this math I'm about to show you on the fly, but it is nice to see how these 2 different equations that you've written down are actually the same thing with just some algebra and concepts taken into account. So here's our Nernst equation, and now let's specify that at equilibrium, the voltage is 0 and Q is just K. Now we just do algebra. We bring over this term to the left side, and then more algebra to just isolate log of K, and then finally, the last step, get rid of the log by doing 10 to the both sides. So let's see how we can use this equation with an example. Our goal in this example is to use these 2 reduction half reactions and their standard state voltages to determine the KSP of AGI. And let's recall what type of equilibrium KSP refers to. It's an equilibrium between a solid compound and its constituent ions in solution. A common mistake in these kinds of problems is to think that the KSP of AGI refers to this equilibrium right here. But notice this is not quite the same as this reaction. This reaction will just be one of several stepping stones needed to actually learn the K of this reaction here. So plan on writing 4 reactions in this example, starting with these 2 here and their voltages at standard state. Pause the video so you can write it all down. So this winds up starting like a manipulating equilibrium problem. At the end of the day, we need to manipulate these so that they can add together to give me the reaction of interest. And we can see right now that's not what's going to happen if we just add them as written. Having AGI solid as a reactant, that's good, and the I- as a product is good, but this silver solid, this electron, that's a problem, and then this silver ion needs to be over on the right side. And so hopefully you can see what we need to do. R2 looks good, but R1, that needs to go in reverse. And so let's flip it, and we get AG solid is in equilibrium with Ag plus an electron. And we know what happens to that standard state voltage when we flip a reaction. It becomes the negative of its original value. So negative 0.7993 volts. Notice that I didn't base which of these reactions to flip based on their reduction potentials. I only focused on what is going to allow me to add reactions together to get the reaction of interest. For these kinds of problems, I don't care what's the more energetically favorable process or what should be the cathode or anode. In fact, we're going to see a very unfavorable voltage at the end of this problem, but that's okay, because we're just interested in this reaction, whatever its voltage may be. So let's see what I mean by that. We are now ready to do some adding. We will add reaction 2 and the reverse of reaction 1. And we can see beforehand that some species will cancel, silver solid, and the electrons. And we will indeed be left with only AgI solid in equilibrium with Ag plus and I minus, which is the reaction that we care about. And the voltage at standard state of this reaction will be those two added together. And we will get negative 0.951 little 3. Negative 0.951 little 3, because the problem's not done. That's a terrible voltage, right? Negative. What that means is that this solid cannot possibly spontaneously dissociate to form 1 molar of each of these, since we're dealing with standard state voltages in this kind of a problem. That voltage is saying there's no way this is dissociating enough to produce standard state concentrations of these. It'll be much less than standard state, which we're about to confirm, because the overall goal was to figure out what is the K value for that equilibrium. And let's just put that SV subscript to be precise. And now is the time to use that formula we wrote down previously. This will be equal to 10 to the whatever our N value is. In this case, our reactions only involved 1 electron. Our standard state voltage for the overall reaction is negative 0.951 little 3. 951 little 3. And then we divide by our 0.05916 value. And then we plug it all in, and we get a value of 8.32 times 10 to the minus 17. And that's the problem. And that's a very small K value, which implies that very little of this will dissociate. We will have relatively small concentrations of these two ions, which agrees with what was stated earlier, that we will not spontaneously get these concentrations all the way up to 1 molar. After this comes a clicker, but we will end there.